So welcome you all in the course Wave Propagation through Periodic Structures and Metamaterial. Myself, Dr. Arnab Banerjee, Associate Professor, Department of Civil and Environmental Engineering at IIT Delhi. So if you see, the course has primarily, if you see the course title, that is Wave Propagation through Periodic Structures and Metamaterial. So here, if we see, there are few key points. So first is that wave propagation, then periodic structures, and third thing is metamaterial. So in this complete course, we will discuss these three aspects and we will try to explore that once a wave is propagating through a periodic structure or a metamaterial, how we can able to get different types of properties into it. What are the different types of phenomena we can able to see there? That is the prime exploration in this course. So we will start first with the definition of the metamaterial, then we will go into the wave propagation through periodic structures. Okay, so today's class, first we will discuss on the period. So if I just go into the course detail and the roadmap, so why this course is? So modern civil and mechanical engineering structures increasingly rely on the engineered periodic structure to control the vibration, noise and wave, and also some sort of cases energy harvesting. So in those cases, metamaterial and the phononic structures enables band gap, wave attenuation, energy redirection, and unconventional dynamic properties that go far beyond the classical vibration theories. So here, if you see, the fundamental point is the structural dynamics. So throughout the course, we will use the structural dynamics. So it is very much advisable to all of you that before you do this course, you must have a background of the structural dynamics or theory of vibration type courses. So if you not do that course, please do those courses before. So now if you see the roadmap, so first stage 1, it is the foundation of the 1D discrete system. So we will spend somewhat like week 1 to 5 on that. So here we will basically cover the wave versus the vibration fundamental. Then we will go to the monoatomic diatomic chains, band gap characteristics, metamaterial, different types of metamaterial we will try to see in the 1D context. Then we will do the negative mass, negative stiffness concept. Then in the next milestone, we will go for the damping model in the different 1D systems. So whatever we have studied here, we will try to see if there is some presence of damping, how this thing is going to change, or what are the different properties or phenomena we can able to get there. Now in the next stage, we will have continuous systems analysis and method. So here we have a discrete. If I just make it, here we are having discrete, here we will have it continuous. Okay, so in case of discrete, we can say it is like a lumped, like spring mass, like this type of system. And in case of the continuous, once we are going, we are now started having bar, beam, frames, plate, this type of systems will come into picture. So here we will primarily adopt spectral element method for bar and beams and frames, then thin walled and the tapered structures, frequency extraction. Then we will also see the transfer matrix method. Then we will compare the spectral element and the transfer matrix method in that. Then we will go to the advanced wave behavior. So there we will try to see how actually the wave coupling and the resonators in the beams actually give some sort of meta properties. We'll also explore how the energy transportation is happening throughout the system and what are the concepts of, and we will also see the wave packets, group velocity, phase velocity, those things we will also explain in those things. Then next thing is much more complex. So in those cases, we will go for like characteristic impedance, fundamental of the 2D lattice structure, wave propagation in the 2D lattice, and we will also see the homogenization approach. And with this, we will conclude the complete course here. Okay. There are also several other advancement are there, like for example, non-Hermitian mechanics can be added, active control. Then you can also think non-reciprocal metamaterial, but those context becomes quite advanced. So we are not covering this in the courses. So learning outcome, by end of this course, student will be analyzing, model and interpret the wave propagation, attenuation mechanism, engineered periodic and the metamaterial based structures with the direct relevance to vibration control, structural dynamics and advanced research applications that we can see. So in this course, I will be the course coordinator, Dr. Arnab Banerjee, Associate Professor, Department of Civil and Environmental Engineering, and the teaching assistants are Pranay Singh, Somendu Saha, Tanmay Kumar Sharma, and Parthojit Mallo. So this is the course content. As I already show you the roadmap. So if I just go to the course content, so there you can able to see. So wave propagation in 1D discrete system, that will be week 1 to week 5. And these full things will be covered there. Then wave propagation in continuous system, that is week 6 to week 10. Then energy transportation in the structural member, that is week 11. And week 12, that will be only the two-dimensional lattice structure. Although this 2D wave propagation is like a very vast, and obviously with the 2 weeks it's like with the 1 week it is very less, but you can understand it is just to give an introduction to that. Definitely the full research domain is actually left behind these full things. Okay, so with this, let me first introduce what is the metamaterial. So if you see the core concept, it is that metamaterial are the artificially engineered material system that are designed to exhibit the physical properties not found in naturally occurring material. Okay, the prefix meta, it is a Greek word which is known as the beyond. So significance of material that are giving some properties and beyond those natural properties is actually called as metamaterial. So these are some of the lattice structures I have shown here. They are giving in some sense some different type of properties. For example, if you think like the fundamental distinction is the conventional material governed primarily by the chemical composition, atomic and the molecular bonding. But in case of metamaterial, properties are governed by their internal structure and architecture, driven by the geometry, arrangement and intrinsic properties of the unit cell, relies on the periodic repetition of these engineered structures. Now, length scale condition. So that is like sub-wavelength structuring. It is also very important in that case. So like once the unit cell, whatever you are looking at, so that must be significantly smaller than the wavelength of the application, and so in that case you can actually homogenize the full property. So if you are try to understand that fact, you can think it like this way, that if you are like in your childhood, maybe you people have seen there in the pond, if you are dropping the stone, you can see that the ripples of the waves are actually propagating. Now if you put a small like a paper boat, you can see that paper boat will go up and down with the wave fronts. So as the wave is moving, this will go up and down like this. It will hardly change the wave front pattern. Like if you see, like suppose maybe if I just draw. So what I was telling, that the sub-wavelength scale condition, suppose if you think like, let's say this is like a pond and you are dropping a stone here, so you can see that wave fronts are propagating like this way. Now let's say you have a small boat here. Let's think there's a small boat here. So what you will see, that this boat will move up and down, and you cannot you see like very slight changes. Maybe you can see at the back side. So primarily the wavefront will still continues like this way. Hardly you can see any differences. But if you are putting a larger boat, like instead of that smaller, like let's say you have a large object and you are dropping that thing here, then what will you see? You will see that the wave is started scattering from here. So that thing actually creating quite different scenario, and therefore it is actually changing the full pattern. So that's why you can see that, like in the first case that object was small, so here the object is small, but here the object is, what can we say more scientifically, this is my wavelength, like a wave is going, so this is my wavelength. Now if the size of the object, let's say this much, so which is very much less compared to the size of the, compared to the wavelength, like let's say this size is, let's say d, wavelength is lambda, so suppose d is quite less than lambda, then what will happen? Wave cannot see that particle, or you can see what, that particle is there, but wave field does not get changed due to the presence of that object. Agreed? Okay. Now you can think that once the object is large, then what will happen? Then the wave is going, and now the wave is started scattering from that object, and it start interacting with that object. In that case, what is happening, like you are having this, but your object size is like that, so it is start modulating the wavefront, and there you are having some sort of scattering effect. Okay, now in case of metamaterial, once we are talking, we are looking primarily for this case, not this case. Okay, so once we are trying to engineer the complete medium, we should make the intrusion or the change of arrangement in such a manner that they are sub wavelength. Make sense? So if your changes is more than the wavelength, then there will be scattering, and you cannot able to homogenize the medium. Homogenization in the medium is not possible in those cases. So that is one of the prime issue, and that is the sub wavelength structuring. I hope you got that idea what is sub wavelength structuring. Then the point is coming homogenization. So homogenization is telling what, like suppose let's say in our medium we have this type of geometry. Okay, now solving that full medium with this type of so much intricate details is actually very difficult. But what do we more prefer? Like let's say somebody gives me a 2D, like somebody like and tell me that this is my field and I'm applying some forces here, it is like fixed at this portion, maybe you are having some sort of boundary condition here, you are applying some other forces like this, and they want to solve it. So what type of property you want to apply there? What type of thing will you look for? So suppose if it is a 2D plane stress or plane strain, like we more interested to see it as like a continuum. So if somebody gives me Young modulus, Poisson ratio, I would be very happy. I will just make a stress strain matrix. Then we will have a strain displacement matrix and we will solve that full thing. But with this type of configuration, what is happening? That matter is not that simple. So suppose if somebody gives a cut portion like this, with some boundary condition here and applying some forces like this, that's not a matter of joke to solve. So that type of cases, we try to find out what can be the equivalent Young modulus, equivalent Poisson ratio for this type of geometries, and these are known as the homogenization. Okay, so if there is no doubt, then we understood primarily. Now why metamaterial? So now structure driven phenomena, like a thumb of the emergent phenomena, like a properties arising from the collective dynamic responses of the system rather than the material points themselves. Key mechanism like periodicity, backscattering effect allows for the wave attenuation and band gap. Local resonances, that is embedded resonators, create a narrow frequency band gap at the wavelength much larger than the structural size. So if you see now, like in this case, we can able to see that like you can see that like we have a mass, and internally we are putting some masses. Then again, after certain distance, we are having another mass. Again, we put some internal structure there. So like this way, we are making it. So you can think that like in case of the acoustic application, that is very common. We having like a wall. In the wall, then we put another wall with another leaf. Again, we put another leaf. Again, if we put another leaf, then if we see that sound transmission, it is something like mass, again another mass, again another mass, again another mass. So which is basically periodic structure. But now you are putting some resonator here. So suppose some spring mass, again some spring mass, again some spring mass, again some spring mass here. And that will be resemblance to what you are looking at here. And this structure can able to give the negative effective mass. I will come into how the negative effective mass is coming, but just for time being, just take that will give the negative effective mass at certain frequencies. Yeah, it is correct. It is correct. It is effective mass, and here it is frequency. So you can see that effective mass is here, and here it is frequency. So you can see that in this range, in this frequency band, your effective mass of the structure becomes negative. And here effective mass is become so high. Okay, so I will come into and I will show and we will calculate also how these things are actually happening, and we can able to see that these things are, maybe it seems quite like ambitious that wow, we are getting negative effective mass, but please understood, we are not talking about the thermodynamic mass become negative. No, it is effective mass, which is something similar to inertia. So here the inertia becomes negative primarily, but this was called as negative effective mass. So we are just using that term negative effective mass, but it is primarily the negative inertia. Okay. So this type of thing we can see. So that is primarily the local resonance behavior. So this actually happens due to the resonance of the internal structure. So in those frequencies, basically the resonance occurs, and it gives like a this type of phenomena. We will do that full calculation. We will do. Don't worry. Now the unique properties of the, so that is the negative properties. So negative refractive index, negative effective mass or stiffness, and the wavelength control and the sub-wavelength control. So these things we can able to see. So now negative refractive index is primarily the property of the electromagnetic and acoustic waves. In the mechanical vibration type wave, we cannot directly see that. Then negative effective mass and stiffness, that is achieving the dynamic properties, is impossible in the static continuum mechanics. Then sub-wavelength control, the ability to manipulate and attenuate the guide wave at the low frequencies without requiring the massive physical behavior. That is our unique physical capabilities of that. So you can see some of the other type of the structures. So here you can see this is a representation of the negative stiffness. Like if you are exciting these structures, obviously dynamically. In metamaterial also you can see some of the metamaterial, some of the particular properties are generated only in the dynamic case with some specific frequencies. Maybe you will not get that type of phenomena for other frequencies. Like here you see, if you are dealing here, it's acting like a normal material. It has a positive mass, so not a big deal. But if you are acting here, yes, that gives you a negative effective mass. And here also, once you are having that negative stiffness, so you are exciting that structure, you can found that once this structure is going to the resonance, then full thing is moving in the opposite direction. So it is something like you are pushing the structure, but in return, instead of having some sort of thrust on you, it is opposite way. So your stiffness become negative in that with the frequency. So in those frequencies, your stiffness is getting negative. Okay. Then in case of the refractive index also, you can sometime able to see that, like normally the wave should go like this way, but you can see that the energy associated with that wave is going to the negative direction. We will do that once we will study the 2D. These are actually quite difficult thing to visualize and understand as well. Then some sort of, and then we have a auxetic material also. So that auxetic material shows the negative Poisson ratio. Like if you are pulling some material, what will happen in case of the normal material? So suppose if you have this material, now suppose if you are pulling it, what will happen? How its deformed shape should look like? Then, am I right? Yes. So that is the case once your material has positive Poisson ratio. You will pull, side is shrinked. Or vice versa, if you push the material here, your side will bulge out. Agreed? But with in the auxetic material, that thing is opposite. Why? Like in that case, what happening? You have your structure like that. You pull the structure. What will happen? It will be bigger. Why? It is not that your material is getting extended or something. It is the geometry. The way it is there, it actually do that. So suppose if you think one structure like this, like if you are making a continuum like this manner, so now think, if you are pulling that structure, what will happen? Like think like full that continuum is made with this type of geometry. Now if you pull it, how that will work? Exactly, the things will open up. That means if you think this link will go somewhere here, this link will go somewhere here, and it will go definitely. This link will go, when this will first shift it little bit and then it will go like this. So you can see that the volume or the area is actually getting extended in both the side. So it is, mean, now if you think that okay, whether the bulk modulus is getting increased, no, you should not think it like that way, because there is a void internally, there is no material. It is like whatever the way you are looking at, now it get expanded in that way. So now if you see that overall Poisson ratio of that material, it is expanded, or that Poisson ratio become negative Poisson ratio. Okay, so engineering application. So now if you think, what are the engineering application it can do? So first of all, like vibration isolation. So in the mechanical and structural engineering, we can think the vibration isolation. Use a periodic resonator based structure to suppress the specific vibration frequencies in machinery. Then lightweight, high strength lattice designed for the shock absorption and the crossworthiness. Then the tailored dynamics, that is the structures with programmable stiffness and the damping characteristics for aerospace component. So these we can think like some of the applications. So primarily we can have that type of reputation in that. Then some sort of civil or infrastructure side, like a seismic protection, like seismic wave attenuation, that is that reducing the amplitude of the earthquake induced ground motion before they reach to the critical infrastructure. Redirection, the cloaking of the building by guiding the surface wave and the body waves. Application areas, high-rise building, long-span bridges, nuclear power plant, etc. People can able to use this type of structure. No, good. So now historical development. So now if you see early conceptual stage, 17th to 19th century, origin of the wave propagation concept in discrete and the periodic system, Newton's discrete spring mass representation for the sound propagation in gases. So these are, you can think that like quite early concept of like a wave propagation through the periodic medium type thing. Although we have not come into the wave propagation to periodic, but as you already seen that in case of the metamaterial, primarily this unit structure is get periodically repeated. So therefore that periodic structure is also very well connected. Now if you think in our real life, we are almost surrounded by the periodic structure. For example, if you take your cloth, look at that carefully, whatever it is, you can see that the fabrics, and the fabrics are very well periodically arranged. If you think the book, pages, they are also periodic. Like think whatever, like also the tiles type, although these are just made for designing, but still people have made it like a periodically. So we are like more or less surrounded with the periodic thing. Very rare you cannot find something like which are not following the periodicity, or if it is not following, there are also still some sort of aperiodicity, but it is some sort of deviation from the periodic structure. So primarily we try to make the things periodic. That's like a primary point what we try to do. So therefore like that periodic thing is also quite interestingly thing. Then the mathematical and physical foundation in the late 19th and the early 20th century, there is emerging the solid state physics, electrical circuits and the radio electronics. Then the Floquet theorem for the waves in the periodically inhomogeneous medium. Then the blocks extension and 2 to 3 dimensional periodic structures. Then engineering driven periodic structure, that is the use of the periodic structural element in the aviation and the shipbuilding, analysis of the periodically stiffened beams, plates, cells, introduction of the dispersion relation, passband, stopbands, and application of vibration, noise control and the fatigue analysis. Then advanced metamaterial concept, that is 2000 and present, that is the artificial engineered periodic material with the tailored wave propagation, electromagnetic, photonics and acoustic metamaterial, negative refraction, wave focusing, enhanced absorption, wave finite element method and application oriented designs. Those also came in that time. So primarily if you see that mechanical type of metamaterial and all those things, that concepts are primarily coming into this portion. Previously it was mostly periodic structure, and few development happened in this range, but in the metamaterial community but that was mostly on the electromagnetic domain, not in the acoustic or mechanical domain. Okay. So now importance. So importance of the metamaterial. So if you think that enable the development of the advanced material with the physical properties not achievable in the conventional materials. Material behavior governed by engineered structural configuration rather than chemical composition. So what I told, that material is immaterial. So if you make this pattern with gold, if you make this pattern with wood, if you make this pattern with steel, inherent effect will be remain same. Definitely your Young modulus will be dependent on the material property. That is fine. But the ratios, they will primarily depend on the configuration. Okay. Then provide the precise control over the wave propagation, mechanical response, and energy interaction. Play a crucial role in vibration control, wave mitigation, and structural dynamics. Improve the seismic resilience, noise reduction, impact resistance in the civil and mechanical structures. Support advancement in the energy harvesting, biomedical devices, and the communication systems, and contribute to safe, sustainable, and multifunctional solutions for modern engineering and the societal needs. So these are some of the things. Now, if you come into the different types of metamaterial, so there we can think first like elastic metamaterial. So in case of the elastic metamaterial means we are talking with the wave where like elastic wave type thing. So here negative stiffness metamaterial, this exhibits the negative stiffness. Once we are applying the force, we can able to see that its response is quite different in that frequencies. Then structured elastic metamaterial. So structural metamaterial employing the engineered lattice microstructure to achieve the tailored mechanical properties, enabling the lightweight, high strength design and customizable stiffness and the flexibility of the medical. And seismic metamaterial can be engineered to control the seismic and the ground bound vibration. It can be also used for the railway vibration control, enabling the foundation system, mitigating the impact. So those cases people are also able to use that. Then it's coming the acoustic metamaterial. So acoustic metamaterial, it is like a negative indexed acoustic metamaterial. So primarily that was dealing with the elastic wave. Now it is dealing with the acoustic wave, sound and all those. So in that case, primarily you can think that with acoustic band gap, so it should gives you some band gap so that in those frequencies the wave is not coming. Like for example, you want to make some building wall, and you are looking that okay, these type of frequencies are generally coming through the wall. So you can try to infuse some of the metamaterial structure in your wall system so that it can able to reduce the vibration. That you can able to think. Then anisotropic acoustic metamaterial. So in that direction of the wave propagation, that is different, like wave propagating in the one direction and wave propagating other direction, they will be different. So that is the anisotropicity is coming. And then the other metamaterial which we will not discuss in this course, that is electromagnetic, magnetic and quantum. But that is beyond the scope of that. In this course, we will primarily refer to the book written by me. So you can see that there's a book also. If you wish, you can purchase that. Or I think it will be also available in the library. So with this, I would like to thank all of you for today's lecture, and we can do it, and we can go far details, like first the introduction to the waves in the periodic structure from the next class onward. Okay.